It's not some cutting-edge new technology or futuristic AI that's pushing the limits of our understanding at the farthest edges of the solar system. Surprisingly, it's actually a machine that's older than most people watching this video. Imagine this, an old spacecraft with an onboard computer that has even less memory than the tiny chip inside your car key fob. It sounds unbelievable, but it's true. This spacecraft still uses 8-track magnetic tape from the 1970s, a technology most modern kids haven't even heard of. And yet, somehow, this antique machine is still quietly sending back data from the far reaches of space. This is the strange reality of deep space exploration. Out there, beyond the warmth of the sun and the reach of modern spacecraft, missions take decades, not days or months. Technology becomes outdated long before it reaches its final destination. But even in this difficult environment, one machine stands out for its unmatched longevity and resilience. We're talking about the legendary Voyager 1 probe, launched nearly 45 years ago along with its twin Voyager 2. These spacecraft became the first human-made objects to ever enter interstellar space, achieving a feat that was once only imagined in science fiction. Just imagine this: when NASA sends a signal to Voyager 1, it takes over 21 hours to reach it. And when Voyager replies, it takes another 21 hours to get that data back. That's a round trip of more than 42 hours. That's because this tiny spacecraft is now over 23 billion kilometers away from Earth. For comparison, it only takes about 20 minutes to send a signal to Mars. And even more amazing, Voyager 1's antenna is just 3.7 meters wide, and its transmitter is as powerful as a regular refrigerator light bulb. The fact that we can still communicate with Voyager 1 after all these years and across such an unimaginable distance is mind-blowing. But what makes it even more incredible is that this probe is still using technology that's practically a museum exhibit today. The systems that run Voyager 1 and Voyager 2 are older than the internet, older than smartphones, and older than most of us. And yet they're still going strong. That tells us something profound about the skill and foresight of the engineers who built them, and the power of smart, minimalist design. So how did the engineers pull it off? What secrets lie inside these aging yet powerful spacecraft? I'm Alex Molin, and you're listening to the Astrum podcast. Today we're diving deep into the remarkable engineering behind the Voyager probes. We'll explore how a few bold design choices, carefully planned decades ago, turned these simple machines into the longest operating spacecraft in history, and some of the most successful missions NASA has ever launched. Originally, the Voyager probes were only supposed to be operational for 5 years. Their main mission was to explore Jupiter and Saturn, along with some of the larger moons around them. But even in the early stages of planning, the engineers had a feeling that these probes could do more. They made certain design choices to prepare for the possibility of an extended mission, even if no one knew for sure whether that would happen. Their gamble paid off, and what was once a 5-year mission has now lasted more than 4 decades. Let's rewind for a second. After Voyager 2 completed its flybys of Jupiter and Saturn, the team decided to push the boundaries even further. They added Uranus and Neptune to the mission plan, and Voyager 2 became the first spacecraft to visit those 2 outer planets. After that came the boldest phase yet, the Interstellar mission. This was NASA's way of officially turning Voyager into an explorer of the unknown, sent to study the outer boundaries of the Sun's influence and eventually pass into interstellar space. This next part of the journey would take the probes to areas of the solar system no one had ever seen up close before, places like the termination shock, where the solar wind slows dramatically, the heliosheath, which is denser and hotter than expected, and finally the heliopause, the outer boundary where the Sun's influence ends and interstellar space begins. These regions are incredibly difficult to study, so the Voyager probes became our eyes and ears in the darkness, far beyond Pluto and the known planets. One of the most important decisions the engineers made was about energy. Unlike most modern spacecraft that rely on solar power, Voyager couldn't do that. The Sun's light is far too weak at those distances. So instead, each Voyager probe was equipped with a radioisotope thermoelectric generator. This device converts heat from the radioactive decay of plutonium-238 into electricity. It's not a huge amount, just 157 watts at launch, which is barely enough to power a laptop, but it was more than enough to keep the essential systems running. These generators lose power slowly over time, cutting in half about every 87.7 years. That decline is predictable, and NASA knew that the probes could stay powered until at least 2025. That's over 48 years of continuous operation. Not bad for a spacecraft that was only meant to last 5 years. And this power system wasn't chosen randomly. When Voyager launched in 1977, NASA had a unique opportunity. The outer planets were going to align in a rare formation that happens only once every 176 years. This alignment allowed the spacecraft to use gravity assists to slingshot from one planet to the next, conserving fuel and increasing speed. But this also meant time was short. NASA had to act quickly. They didn't have time to plan follow-up missions. And Congress wasn't eager to fund a full-scale grand tour of the outer planets. So the Voyager team made a bold choice: build the probes to last longer than needed just in case. They optimized every part of the spacecraft for durability and hoped that maybe, just maybe, the funding and support would come later. Each Voyager probe carried 11 scientific instruments. To increase reliability, many of these instruments had built-in redundancies, backup systems that could be activated in case of failure. To navigate and stay oriented in space, each spacecraft was equipped with gyroscopes, star trackers and 16 hydrazine thrusters, 8 of which served as backups. These backups proved their worth when Voyager 2's main thrusters stopped working after nearly 4 decades. NASA switched to the backup thrusters, and they worked flawlessly, even after sitting unused for 40 years. The spacecraft also had 3 onboard computers, each with its own task. There's the Command Computer Subsystem for processing commands from Earth, the Attitude and Articulation Control Subsystem, AACS, for keeping the antenna pointed correctly, and the Flight Data System for handling scientific information. These computers aren't powerful by today's standards. In fact, they're incredibly simple compared to even the cheapest smartphone. But what they lack in speed, they make up for in reliability and design efficiency. The AACS, for example, is responsible for keeping the spacecraft's antenna pointed precisely toward Earth. This is critical because the signal from Voyager is incredibly weak. If the antenna isn't pointing exactly at our deep space network, communication is lost. And the transmitters only have the power of a refrigerator light bulb, just a few watts, so every bit of accuracy counts. If the probe were to drift even slightly, it would vanish from our reach like a whisper lost in a thunderstorm. The spacecraft also had a clever way to store and transmit data. Each Voyager probe came with an 8-track digital tape recorder. Yes, just like the old music tapes from the 70s. This device could store about 536 megabits of data at a time, which was enough to hold around 100 images. While that might sound tiny today, it was a massive leap from the earlier Pioneer probes, which had no onboard data storage at all. These tape recorders were built to last, and remarkably, they did. Voyager 1's recorder is still working even now, though Voyager 2's was shut off in 2007 to conserve power. It's surprising to realize that the most significant leap in our understanding of the edge of our solar system isn't coming from some flashy, modern, cutting-edge technology. Instead, it's coming from an old, worn machine, an engineering marvel launched decades ago. Its onboard computer holds less memory than the chip inside your car's key fob. And incredibly, it still uses 8-track magnetic tape technology that belongs to the 1970s. That's older than many people watching this video right now. It's a strange contradiction in space exploration. As we reach deeper into the cosmos, the technology we rely on often becomes outdated before the mission even starts. And yet, it's this very old tech that's revealing some of the deepest secrets of our universe. That aging but record-breaking machine is, of course, the legendary Voyager 1 spacecraft. Along with its twin Voyager 2, it became the first man-made object to reach interstellar space, a feat that still boggles the mind. Today, when NASA sends a signal to Voyager 1, it takes more than 21 hours to arrive. That's because the spacecraft is about 23 billion kilometers away. For comparison, it takes only around 20 minutes for a radio signal to reach Mars. Even more astonishing is the fact that Voyager 1 is still communicating with Earth using a 3.7-meter wide antenna. That tiny piece of equipment is sending signals over unimaginable distances, and we're still able to receive them, barely but clearly enough. What makes this even more incredible is the fact that the Voyager probes rely on technology that would be more at home in a museum than at NASA's Jet Propulsion Laboratory. So, how is it that such seemingly outdated equipment has not only survived but thrived for nearly half a century? To understand this, we need to dig into the design choices made by the engineers who built these machines. The Voyagers were built to last, to endure, and to explore. And while the technology might seem primitive now, the brilliance of the engineering has stood the test of time, beating records, pushing boundaries, and continuously rewriting history. I'm Alex Molin, and you're listening to the Astrum podcast. In this episode, we're diving into the remarkable technology behind the Voyager probes. We'll explore the clever engineering decisions that made these spacecraft nearly indestructible, and we'll see how foresight and careful planning enabled them to carry out the most ambitious and successful deep space mission humanity has ever launched. These aren't just metal shells drifting through the void. They are symbols of human ingenuity and a testament to what's possible when engineering meets vision. Originally, Voyager 1 and 2 were only supposed to operate for 5 years. Their primary mission was to study Jupiter, Saturn, and the larger moons orbiting these gas giants. That's it. Just a quick tour and then silence. But the team behind them had bigger dreams. They made design decisions that quietly opened the door to a much longer, much grander adventure. And when the time came, these choices made it possible to extend the mission far beyond its initial goals, turning what was supposed to be a brief exploration into an odyssey across the solar system and beyond. After completing their objectives at Jupiter and Saturn, the Voyager 2 team proposed something even more daring. Why not continue on to Uranus and Neptune? NASA agreed, and Voyager 2 became the only spacecraft to visit these two distant planets. After that success, the mission evolved yet again into something unprecedented: the Interstellar mission. The goal now was to explore the outer limits of the Sun's influence. Regions like the termination shock, the heliosheath, and eventually the heliopause, which marks the boundary between our solar system and true interstellar space. These places had never been explored before, and the journey would push the probes to their absolute limits. A huge part of what made this possible was the energy source selected for the Voyagers. Each spacecraft was equipped with a radioisotope thermoelectric generator, or RTG. This device converts heat from decaying plutonium-238 into electricity. At launch, each RTG produced around 157 watts of power, enough to run a laptop or maybe charge a mobile phone. That might not sound like much, but for Voyager it was more than enough. The spacecraft was designed to operate with extreme efficiency, and the slow decline in RTG output was factored into its long-term mission planning. It meant that even decades later the probe would still have enough juice to keep going. This long-term energy planning wasn't just luck, it was a calculated move. Back in 1977, when the Voyagers launched, NASA had a rare and fleeting opportunity. The outer planets were lining up in a way that happens only once every 176 years. This alignment allowed the spacecraft to visit Jupiter, Saturn, Uranus, and Neptune in a single journey, using gravity assist to boost their speed without using extra fuel. But this also meant there was no time to waste. NASA couldn't wait around for funding to be approved for a grand tour mission. So, the Voyager team made a bold decision. They would build the spacecraft with capabilities for a longer mission, even if the official budget didn't cover it, just in case. Every detail of the spacecraft was designed with durability in mind. Each Voyager carries 11 scientific instruments, many of which have redundant systems. If one component fails, another can take over. The probes also have gyroscopes to help maintain orientation, and 16 hydrazine thrusters, 8 main thrusters and 8 backups. That backup system proved its worth in 2017 when Voyager 2's main thrusters stopped working after 37 years. The team switched over to the backup thrusters, which hadn't been used in 4 decades, and they worked flawlessly. That kind of reliability doesn't happen by accident. It's the result of deliberate, thoughtful engineering. The onboard computers are also a marvel, even if they seem laughably outdated by today's standards. In 1977 they were cutting edge. Voyager's imaging system is controlled by the Computer Command Subsystem, which runs fixed programs for things like fault detection and error correction. Another essential computer, the Attitude and Articulation Control Subsystem, is responsible for keeping the spacecraft pointed in the right direction. And no, it doesn't give attitude, it manages the probe's actual orientation relative to Earth. Without this system, the high-gain antenna wouldn't be able to maintain contact with NASA's deep space network. Speaking of antennas, let's talk about that 3.7-meter dish on each Voyager. It's responsible for sending and receiving signals across billions of kilometers. The transmitter only has the power of a refrigerator light bulb, and yet its signals are still being received here on Earth. That's only possible because both NASA and the spacecraft are precisely aligned, like two dancers locked in a cosmic routine. But there's more. Each Voyager also has an 8-track digital tape recorder capable of storing 536 megabits of data, enough for about 100 images. That might seem small compared to your phone's storage, but it was a massive leap forward compared to earlier probes, which had no onboard data storage at all. The company that made these tape recorders, Edix, claimed they could process more than 4,000 kilometers of tape without any visible wear. And they had to be tough. These recorders were built to survive some of the harshest conditions ever encountered by a machine. Temperatures fluctuate, radiation is constant, and there's no one to fix them if something breaks. And yet, they performed perfectly. Voyager 1's digital tape recorder is still functioning today. Voyager 2's recorder was turned off in 2007 to conserve power, but that decision was part of a carefully managed strategy to extend the mission's life as long as possible. Durability wasn't just about internal systems either. The Voyagers had to survive physical threats as well. One of the most terrifying parts of the journey was passing through the asteroid belt. In the early days of space exploration, scientists believed this region was densely packed with rocks that could tear a spacecraft apart. But the earlier Pioneer probes had made it through, and that gave Voyager's team the confidence to try. It paid off. Both Voyagers passed through the asteroid belt unscathed, revealing that it's mostly empty space. That success was crucial. If the probes hadn't made it past that obstacle, the rest of the mission would have ended before it even began. But even after all those hurdles were cleared, new challenges appeared in the vast, empty regions between the planets. The biggest of these was the extreme cold of interstellar space. NASA equipped the probes with multiple heaters to keep their systems from freezing. But as the power levels declined over time, those heaters had to be turned off one by one. 2 years ago, the heater for Voyager's cosmic ray detector was shut down. Temperatures inside that component dropped by 70 degrees Celsius. Everyone assumed the instrument would fail, but it didn't. It kept working flawlessly. That's a level of resilience no one expected. Despite the probe's incredible endurance, not everything has gone perfectly. Just a few years ago, Voyager 1 started sending back strange, scrambled data. Telemetry signals, essential information about the spacecraft's status, were suddenly filled with gibberish. It turned out that the attitude and articulation control system was failing. While the rest of the spacecraft was operating normally, its speed, position, and even signal responses were all fine. The telemetry data made no sense. It was like the spacecraft had lost its sense of direction. Thankfully, the engineers found a workaround by switching to a backup computer. But as you can imagine, there won't always be backups available. Still, we have so much to be grateful for. Voyager 1 has traveled farther than any human-made object in history, and its discoveries have forever changed how we see our solar system. Its primitive technology has proven that you don't always need the latest tools to achieve greatness. Sometimes, smart design and a lot of patience are enough. Eventually, the day will come when both Voyager 1 and 2 go silent. But when they do, they'll leave behind a legacy unlike anything else in space exploration. They were never just machines, they were ambassadors of Earth, whispering back stories from the edges of the unknown.